Good morning, good afternoon, good evening. Whenever you are watching this video, let me welcome you all to our channel Future Endeavors. Okay, so we have been discussing about electromagnetic induction in the last lecture. We have just started the topic. Today we will be carrying on with the discussion of electromagnetic induction and we will be briefly discussing about the comparison of AC and DC. I think you have heard this term AC and DC. AC means alternating current, isn't it? You have always heard that the supply AC is 220 volt, isn't it? So you have heard this term AC and also you have heard the term DC. So what actually it is, we will be discussing it today in our lecture. So let us just quickly move on to our topic without wasting much time. I hope you are all enjoying our videos. Please do comment in the comment section. If you are free to ask any kind of questions regarding our lectures or anything that you don't understand, you can mention in the comment section. We will be definitely trying to solve your problem and we will be very happy. Actually, we will be very happy if we can solve your problem. Okay, so let us just quickly move on to the topic electromagnetic induction. So what is electromagnetic induction? In the just previous class we have started this topic electromagnetic induction. Okay, so what is this? What is electromagnetic induction? I think the brief idea is clear, isn't it? We have talked about that when you cause a current to flow through a conductor, what happens? It creates a magnetic field around the conductor, isn't it? Likewise, in the reverse way, think of it like this: that if you place a conductor in a magnetic field and if you move the conductor, if you apply energy mechanically, if you apply mechanical energy and move the conductor, definitely it has been observed that the reverse thing, that is a current is seen to be flowing through the conductor. That is, you can other words say that an EMF is generated within the ends of the conductor, and if it is connected to a circuit or to a closed path, then we see or we observe that current flows through it. So this is the simple concept of electromagnetic induction. So how can you define electromagnetic induction? So we can just write it like in this way that when a conductor is moved, in a magnetic field, when a conductor is moved in a magnetic field, it is observed that an EMF, I hope you all remember the full form of EMF, electromotive force. An EMF is induced across the ends of the conductor, and if it is connected to a closed circuit or closed path, rather I can say to a closed path, that is a circuit, closed path, in bracket you can write it as circuit, then current flows through it. Okay, then current flows through it. Okay, so this is the concept of electromagnetic induction. Just you can note down the definition, it will be helpful to you. Okay, so this is electromagnetic induction. Now this electromagnetic induction was basically observed by Michael Faraday. Okay, and he stated law regarding this electromagnetic induction, regarding this process of electromagnetic induction. What did he say? He said just whatever we have written in this definition, basically this was what he actually tried to say, that whenever there is an relative motion in between a conductor and a magnetic field. Why I am saying that relative motion? This is because you can keep the conductor at rest and move the magnetic field, or in the other way you can keep the magnetic field at rest and move the conductor, both way. That is, there must be relative motion between the conductor and the magnetic field. Then it is observed that this kind of phenomenon happens, that a current is induced, an EMF is induced in the coil, that is a current starts flowing through the coil whenever such a coil is or a conductor is connected to a closed path. Okay, so this is electromagnetic induction, and this concept was introduced by Michael Faraday. So this is also known as Faraday's laws of electromagnetic induction. Okay, so what are the so can you just think of what are the laws that Michael Faraday actually said regarding the electromagnetic induction? He said that whenever there is a relative motion in between the conductor and the magnetic field, there is an EMF induced in the coil, and if this coil is connected to a closed path, a current starts flowing through it. Okay, so this is the very basic law of electromagnetic induction. Okay, and it has been observed that more is the relative motion between the conductor and the magnetic field, more is the EMF induced. Okay, so lesser is the speed, lesser is the relative motion, lesser will be the EMF induced, and more is the relative motion, more will be the EMF induced. Okay, so I think this concept is clear. So this is the Faraday's law of electromagnetic induction. Okay, fine. So this is what you can say about electromagnetic induction. Okay, fine. Now see, here is another law, which is Lenz's law. What does Lenz's law say? Okay, so Lenz's law, actually what does Lenz's law states? Okay, Lenz's law actually states that there is a. Okay, now let us see what is Lenz's law. See, actually before saying this law, just let me demonstrate one thing to you. Say consider a conducting wire, a conducting loop like this. Say conducting loop like this. It is hanging from a certain support like this. Okay, so this is a conducting loop. The loop is actually in front of you like this. Okay, like this. Now if I consider, say let me take a loop so that it is easier for you to understand. So if I consider this is a loop, okay, circular loop. So and if this red marker is a magnet, so if you move this red marker, the cap of this red marker is actually the north pole of the magnet. If you move this magnet towards this coil, towards the conductor, okay, so isn't it that the magnetic, there is a relative motion between the magnet and the conductor, isn't it? Say consider this is the magnet, this is north pole of the magnet, this is south pole. Now when the magnet is moving towards this conductor, there is a relative motion between the magnet and the conductor, isn't it? Now the magnetic field lines are like this. Okay, so what actually happens is that the magnetic field lines cut the conductor when you move it or near the conductor. Okay, the magnetic field lines cut the conductor, and as the magnet is moved near the conductor, what happens? It actually is seen that the more number of magnetic field lines start cutting the conductor, and as the number of field lines cutting the conductor changes, EMF is induced. So actual fact is that. Okay, now when you are moving this magnet towards the conducting loop, what happens? A certain polarity will be induced in this loop also. Why? Because as soon as you are moving the magnet towards the loop, what happens? A current starts flowing. And you know, when a current starts flowing in a conductor, it produces a magnetic field of itself. So the same case also happens here. When you move the magnet towards the conductor, a magnetic field is induced. A magnetic field is induced in the conductor also, as because the current is flowing. Okay. Now see, my question is that when the north pole, when the north pole of this conductor is moving towards this loop, a current is induced, it is okay, but in which direction the current will be induced? It will be either flowing in the clockwise or in the anti-clockwise direction. So which direction? Say this is the north pole of the magnet and you are moving this towards the conductor. Now Lenz's law says that, what does Lenz's law says that? Lenz's law says that the current will be flowing in this conductor, in this conducting loop in such a direction that it will produce a magnetic field which will oppose the original magnetic field that is producing the current itself. Is it clear? Just pause the video and just again rewind it and again listen to it. If we just move this magnet towards this conducting loop, it is seen that the current will start flowing in this loop in such a direction that the magnetic field produced that due to that current will be opposing the original magnetic field of this magnet. It will oppose the very cause that is producing it. The current will flow in such a direction that it will oppose the very cause that is producing it. This is Lenz's law. Okay, this is Lenz's law. So actually what happens, the same polarity is induced in this coil, in this phase, the phase that you are seeing. This is the north pole. When the north pole moves towards this, the same north pole is induced in this phase of the coil. That is, you will be seeing in this phase, you will be seeing current flowing in the anti-clockwise direction. Current is flowing in the anti-clockwise direction. Okay, anti-clockwise direction. You will be seeing the current flowing in the anti-clockwise direction. Is it clear? Just for a moment think what will happen if, say, when you are moving the north pole of the magnet and south pole is induced in this phase, the phase that you can see. Okay, what happens? The north pole of this magnet will be attracted by the south pole of this conducting loop, and the magnet, if you just give it a little push, the magnet will keep on moving itself towards this conducting loop, and more the number of magnetic field lines will cut this loop. That is, the number of magnetic field lines cutting this loop will change, and definitely more amount of EMF, more EMF will be induced. So actually what does this mean? That you are doing no work, you are just pushing the magnet little bit and then just leaving. The magnet will automatically move towards the conducting coil and it will generate electricity automatically. So is it possible? No, never possible. It has been said that energy is always conserved. Energy can be converted from one form to another form. So until and unless you spend energy in some form, the electrical energy will not be generated, will not be produced. Okay, so this is the main fact. So this is basically the Lenz's law. The Lenz's law says that, if you just want to write, you can slow down the video and write down the Lenz's law. Lenz's law says that the current that will be flowing in the conducting loop when a magnetic field is changed passing through the loop, the current will be flowing in such a direction that the magnetic field generated due to the current flowing will be opposing the very original magnetic field due to which actually that current is being produced. Okay, so this is the Lenz's law. I think the Lenz's law, concept of Lenz's law is clear to all of you now. Okay, so this is actually the concept of Lenz's law. Fine. Okay, so now we will be moving on to the next topic. The next topic is an AC generator. No, before that I will be briefly discussing the Fleming's right hand rule. Fleming's right hand rule. So next topic is Fleming's right hand rule. Just note it down. Fleming's right hand rule. You are already familiar with the Fleming's left hand rule, isn't it? Now comes the right hand rule. What does the right hand rule says? Now see, we have been saying that whenever there is a change in magnetic field that is in contact with the conductor, there will be an EMF induced. Now in which direction this current will be flowing is also given by the Fleming's right hand rule. Now for this, to apply the Fleming's right hand rule as well as the left hand rule, we have said that the magnetic field, the direction of the current and the force, that is the, here you can say the motion of the conductor, these three things must be mutually perpendicular to each other. So if I consider my right hand and the three fingers, thumb, the middle, the index finger and the middle finger, all stretched out mutually perpendicular to each other, then thumb indicates the direction of the motion of the conductor, in which direction the conductor is moving. The index finger indicates the direction of the magnetic field, and the middle finger then will indicate the direction of the current flowing through the conductor, which is being moved through the magnetic field. Okay, so if I just consider that a conductor is like this, okay, and here you can say that there is a magnetic field in this direction. Say this red pen is a magnetic field, it indicates the direction of the magnetic field, okay, and this is the conductor. And if I just move this conductor in the upward direction, the thumb points in the upward direction, so if I move this conductor in the upward direction like this, okay, like this, okay, and EMF will be induced in this conductor and the current will be flowing from this end, that is the white end to the black end, okay. See, is it clear? So the middle finger indicates the direction of the current flowing through the conductor. So if I just move the conductor like this, the magnetic field is in this direction, it is just pointing towards you, and the conductor is being moved like this, the current will be induced in this conductor from the direction white end to the black end, okay. So this is the Fleming's right hand rule. So Fleming's right hand rule says that if we stretch our three fingers of the right hand mutually perpendicular to each other, three fingers mean the thumb, the index finger and the middle finger, with the thumb denoting the direction in which the conductor is moving, index finger denotes the direction of magnetic field, and middle finger denotes the direction of the current induced, okay. So if we stretch the fingers like this, then the middle finger will give me the direction in which the current will be flowing through the conductor, okay. So this is the Fleming's right hand rule, okay. Now quickly let us move on to the next topic, we don't have much time left, okay. In the next topic we will be just briefly discussing this application of electromagnetic induction. Can you imagine where this principle of electromagnetic induction is being applied? Yes, I think you are all right, all correct. That is electrical generator. Okay, in generator what we do, we apply this principle of electromagnetic induction to produce electricity, to produce electrical energy. So next topic is an generator. Okay, generator. Okay, so generator, what does it do? A generator what does a generator actually do? A generator basically converts the mechanical energy into electrical energy. The generator converts the mechanical energy into electrical energy. Okay, we are moving a conductor, so that is mechanical energy, and that mechanical energy is being converted to electrical energy in this generator. Now what happens in generator? We have two magnets. One is the north pole and one is the south pole. We have two magnets like this. Okay, this may be a horseshoe magnet. Okay, and say if there is a rectangular coil here, okay, like this rectangular coil. Okay, so in between there is two magnets and there is a coil in between here, like this. Okay, now if the coil is being rotated like this through the magnetic field, okay, so I think you are able to understand it, rotated like this, the magnetic field, then obviously when it is like this, the number of magnetic field lines passing through this coil is something and the value, and when this like this, it is different. So there is a change in the number of magnetic field lines passing through the coil, and this change causes an EMF to be induced in the conductor. Okay, so this is the concept of the generator. Now see, this generator, if it is simply taken in this way, and say there are two rings like this, one is here and the one is here, and from these two rings if you just take the output connection, from these two rings if you take there is a brush. Okay, brush means not the brush that you used to brush your tooth, no, not that brush, it's a brush, it is a small, and I think all of you have seen the brake shoe in your cycle. Like that, a small construction is here which is made up of graphite, and from that brush the wire is being taken out. Okay, now this brush is not permanently attached to these rings. Okay, these rings are called the slip rings. Okay, slip rings. Now the brushes are not permanently attached to the slip rings, they are just gently touching the slip ring. Okay, now as the slip ring moves, as the slip ring rotates, the brush does not rotate, it simply is slightly bounded, slightly attached to these rings. Okay, now if you consider here, see, when the conductor is in this position, the current will be flowing in one direction, and when the conductor moves in this direction, the current starts flowing in the opposite direction in this conductor. Okay, is it clear? The current starts flowing in the opposite direction. Okay, it is a little bit difficult for you to understand this because without 3D modeling or 3D picture it is a bit difficult, but if you just think calmly, it will be clear to your mind that when the conductor is rotating, because we will get the direction of the current using Fleming's left right hand rule. Okay, so if you apply that rule, you can see that the current flowing in the coil gets reversed. Okay, and when it gets reversed, is actually what happens? The current first flows to the circuit. Okay, so the current reverses its polarity again and again. Okay, now this reversing of current polarity leads to the reversal of polarity, and this reversal of polarity causes the current to flow in alternate directions within a very little span of time, and this type of current is called actually direct current. It's called alternating current. Okay, when you take a battery, when you consider a battery or a cell, what happens? It causes the current to flow in a single direction. Say this is a resistor, the current keeps on flowing in the same direction. It will not change, the direction will not change. So this kind of current is actually called the direct current, or what is known as DC. This kind of current is known as direct current or DC. Whereas this kind of current that you are getting here is called as AC or alternating current. Okay, so this is the main difference between an alternating current and direct current. Alternating current, the polarity of the current keeps on changing in a very specific span of time, whereas in case of direct current or DC current, the polarity remains the same. Now you will be thinking, how many times can this polarity change? Well, it's quite huge. Because actually what we say that the supply voltage that is coming to our house is 50 Hertz, AC 50 Hertz. What does this 50 Hertz means? It means that in 1 second this polarity reversal, positive to negative and negative to positive, takes place 50 times in 1 second. 50 times in 1 second. And if you just break it up, it will, if you consider positive to negative and negative to positive, okay, so this one cycle will be repeated 50 times in 1 second. So it's quite hard to imagine that yes, within 1 second this can change so many times. Okay, so this is actually the frequency of the alternating current. Whereas if you consider the frequency of direct current, it is 0 Hertz, isn't it? Because in direct current actually the polarity is not reversing. So it's so the concept of alternating current and direct current I think is clear. Direct current has a frequency of 0 Hertz. So this is the concept of current. So today we will be ending our lecture here, okay, because we have no more time left. Okay, now on the next video we will be starting a new chapter, and I hope you have enjoyed our video, and if you have any query, please do mention in the comment section. We will be happy to solve your query. So thanking you all. So till the next video, thank you, goodbye. Okay, tada.